let's compare two-way equation to the one-way equation migration result. When we use a one-way equation, the first element for the equation-based method is a downward continuation, right? So let's see. I showed this PowerPoint before for the downward continuation. So what we do, we have a seismic section in the x direction, time direction, so it's 2D seismic file. What we do downward continuation, we just downward the surface by delta z, gradually from surface downwards, right? So when your surface, if we downward by delta z, so that means the next profile, x the same, but z, t direction will be shorter because you already downward. So the second profile is by downward. That's time axis becomes shorter because your surface, receiver surface, is not on the true surface, actually below the true surface, right? And the next one, even deeper. So this t-axis becomes shorter, right? Gradually reach to the final sample here. So downward continuation in terms of time, you can see this start from time 0, gradually downward, right? So that means every time the profile becomes smaller. So what's the final image of migration? Image is at this time, at this depth, time t equals 0 is the image, because we assume at this depth, the reflector is exploding source. Okay, so this is a downward continuation based on the one-way equation. The reverse time migration is different because in reverse time migration we do not use downward continuation. Reverse time migration we use a proper wave equation, which is two-wave equation, right? So what do we do here? We start from x, y, the order model, right? And in fact, we call it reverse. Reverse means we start from the maximum time. We start from bottom. And the wave propagating backwards. So from here, you back to here, right? So backwards. So the thick arrow here indicates the direction. Okay, you just backwards. That's we're talking about the true wave field, wave field, right? Of course, you need a source field. Source field is just an element, synthetic generally, it's not form field. If we talk about migration, we're just talking about received wave field. It's start from the largest travel time. That's the name, reverse time came from. You start from the largest time, for example, t equal to 6 seconds, and then every 4 milliseconds backwards, right? So when you have a 6 second wave field, you do the cross correlation to the source wave field at 6 seconds. Now, if we move up to the 5 second, you also have the source wave at 5 seconds and do a cross correlation. So this is the way you do that, right? So the image condition of this will be cross correlation instead of a time 0. It's cross correlation, right? So that's migration. In this case, you can see this looks like on the surface, but it's cross correlation, okay? So this is different. I would rather say it's cross correlation. That's probably more easy for you to understand. But for the people who invented this method, they try to avoid to say this cross correlation. They just try to just tell you this true image. That's not true. That's not true. That's from the very beginning of the lecture. I said that we should understand the limitation of each individual step. That's the open door for your future research of it, right? Not only for you do not treat the result as a black box, but also open door for your future research, right? So you keep your eyes and the mind open. That's my process here. We saw this model before. That's actually this result generated by one of my previous PhD students. Actually, it's quite good. You can see the source wave front move downwards, but you also see the wave here. It's not only downwards, but also have wave going back upwards. So you can see the wave field contents. You can see here, boom, you see the wave going back and downwards. So it's not a one-way, it's two-way. For any point, wave transmitted and also reflected, okay? You can see here, for example, this reflection, this transmission, for everywhere, right? So this means this wave field is a four-wave field. It's four-wave field, okay? And if there's internal multiples, they're also there. So including all the wave fields. And then for the receiver port, start from a very extremely end of a time and gradually come back, just like the PPT I showed before, right? So you can see the wave field from here, but just for the long short time. So you can see the wave field gradually gets stronger because they're close to the time zero. Right? Okay, so, and then you do cross correlation, get the final result, just the reverse time migration. Let's do the comparison between one-wave equation and the two-wave equation, or between we call the so-called one-way wave equation method and the so-called RTM. RTM is two-wave equation, okay? Just difference between these two, just the wave equation, okay? So let's see. First of all, for one-wave equation, we do not generate, well, we only generate one downgoing wave, do not generate upgoing wave, right? So this one-wave equation migration does not generate both waves, only generate one. Right, but the two-wave equation, you generate both. So you have secondly, for the dipping feature, or dipping limitation, for one-wave equation, because you have one way, just like you travel to the one direction, you only can image migration angle less than 90 degrees. You do not see the wave come back. So that's why one-wave equation even worse than Kirchhoff migration, right? But for two-wave equation, there's no limits. You wave travel up, down, anywhere, right? For the amplitude, this one actually is amplitude preservation is not, because this is we call the plane wave absorption. Plane wave, we have a source, just like a line source, with angle propagating. Right? In fact, it's cross correlation, but in the same layer, electrically, you see the variation changes. You see the variation, see the amplitude changes, right? But for the two-wave equation, this also includes spherical wave propagation. So it's point source. This one's a line source. That's the difference. And here, this one for one-wave equation does not include the multiples, but for two-wave equation you can include multiples. That's why the image will be more. If velocity right, if model right, you have a much better result. Okay, so the wave propagating downwards to the surface in the black curves, right, wave front, and for the two-way equation, you also have wave reflection back in the curve, in the red curves here, right? So, and the reflection wave front is related to the amplitude. Even though I said the wave field is amplitude preserved, but the final image, I said, okay, final image is correlation, cross correlation. That's the reverse time migration result. If we compare to the one-wave equation, you can see the difference actually is here. Right, this one is not as clear as here. You know, this one under here, because this one is very deep, steep dip, but for the two-wave equation, doesn't matter how steep dip is. They have a very good image, right? Assume this two uses exactly the true model, true velocity model. So there's nothing wrong with the velocity model. Only difference is a one-wave equation and the two-wave equation. For this part, for reverse time migration, you can see the detail of a structure of the top of a solid body. But for the one-wave equation, because you only see the one wave downgoing, you see it does not show the accurate detail structure here, okay? Also here, this one's much clearer, much sharper. I already pointed out here. Right, for the velocity model, looks like this. And the imaging for the one-wave equation, you see the solid body here, but you cannot see the steep dip imaging. But if you use a two-wave equation, you can see the boundaries here clearly, which is RTM, right? Okay, compared to. People, typically modern days, you have a powerful computer facility, you can do this now. Let's see the velocity model. If we compare this is my grand result. That was the only portion, right? But I know the whole profile. If we compare this to the true velocity model, you can see they are actually. So this also gives us indication we do need a good geological interpretation for the velocity model before we do migration, right? See, very clearly. That's the RTM. So in summary here, RTM is best one, blue one here. That can consider vertical velocity variation, lateral velocity variation, anything the steep dip beyond the 90 degree, and currently this is the best in terms of image quality, is the best one. Of course, that's very slow, right? So this is currently the best one. Number of my PhD students that actually work on this, right? This is one very hot topic now. Okay, for the velocity migration, I already said that there are two research directions, but the third one is the velocity. In fact, I already said that migration result depends on a velocity model. So I always say the third research direction is if any of you can propose an algorithm to the migration without the velocity. That's the direction. Velocity independent migration algorithm. 20 years ago, a group of Israel scientists started this research direction, but after a few years, they gave up. That's already done out. But if any of you in the future, you can come up to algorithm for migration without velocity dependent or weak dependency, right? Of course, you do need a velocity, but otherwise it's a travel at least in a different order, right? So how many 1,000 meters per second or how many 100 meters per second, right? That's of course. So at least they started with a weak velocity dependent. That would be very, very good. But nevertheless, in the current status, we all need velocity model. So we know we need to see the effective, the inference of velocity here. So all the algorithms so far I introduced here are velocity dependent. We do need a velocity. Velocity is the essential parameter, right? Doesn't matter how sophisticated of your algorithm, how refined the algorithm, velocity is key. Algorithm, well, should be secondary. Velocity is key, right? As I said, critical for velocity, and velocity depends on the geology, right? So we need for the migration, we need a geological model. So basically, migration is something, you know the model in your mind, and then you generate image to reflect that, right? To double check it, actually. Okay, maybe show some further detail based on migration. So migrations, you have a model already, and then you do the migration. When we talk about velocity, we realize for the point reflector here, that's the scattering, diffraction follows this hyperbolic equation, and this hyperbolic equation is identical to the hyperbolic equation for the velocity analysis for NMO. So that means NMO velocity can be used for migration, right? I already said that before, so I repeat it. Okay, here for NMO, this is the best why we can use NMO first, generate the velocity, and then do the migration. But for layered structure, this velocity for the near offset, for the small offset, this velocity mathematically derived is IMS velocity, root mean square velocity, based on these layers, right? So this is the relationship between the migration velocity and the layered velocity. You can see that. Because this one's formula is very close to the NMO velocity model, NMO equation. So if you have a velocity model with a layered structure, you cannot use the layered velocities straight away for the migration. You do need to calculate the IMS velocity to the migration. That's the way, right? Just for layered, because the difference between the two, one is source and receiver at the same position, just for migration, but for an MO, you just have a source and receiver in different places, right? So in the NMO, the edge here is at half of distance between source and receiver, and in the migration, the edge here is the horizontal shipping. Source receiver point here, but the reflector point here, right? You can see the horizontal shipping. That's the mathematical formula are identical, but the physical meaning different, edge here different. So commons here, stacking summer over hyperbolas. Diffraction stack also summer over a hyperbolic curve, right? So NMO generate a stacking velocity. This stacking velocity can be used for migration because they have the same formula. Also, the edge is different, right? One in NMO edge is half the distance between source and receiver point. But for the migration, H is actually the subsurface point shift from a CMP point. However, they have an identical mathematical equation, so we can use the velocity, right? The velocity is measured on unmigrated data. That's a stack section we showed before. We have a bow tie structure. We have a deflections. We have a good result of migration because we have a good migration velocity. So velocity is important. But if you have a wrong velocity, for example, lower velocity, which is over migrated, and this one is not fully focused, right? It's not fully focused. If a high velocity under migrate, that's also not right, right? So that's the velocity inference. So a factor of a velocity errors, either degraded image or and degraded focusing. So focus is not so good. That's the velocity. Too low will be under migrated. Too high will be over migrated. Okay. And if we use that one, we reviewed for the post-stack migration, but for pre-stack migration, that means if we do the stack, because when we do pre-stack migration, we do the gather by gather, right? The final image, we should stack them together. So in the stack, there will be misstacking. Let's show you an example. Okay, let's see NMO first. Just NMO hyperbolical before NMO. After that, ideally it should be flat. If we lost too low, that'll be overcorrected. If we're too high, it's undercorrected. Right, this for the NMO. Same phenomena happen for the migration. It's either time or Z axis. So velocity too low and the velocity too high. But if we have a right velocity, so you do need to tune in the velocities, right, based on the image gather. If this image gather appear like this, you should increase velocity. If image gather look like this, you should decrease velocity, and then have finally iteratively finally get a good velocity. You have a flatter. So this gather here is called CMP gather, and it's not CMP. It's called common image gather, CIP gather, common image gather. Right? Let's see example. That's a sort body, a flat layer here. And this use a true velocity model, you generate a very good image. Well, apart from my age factor, right? But the majority part is good. Typically here, you can see that. But if we use a long velocity, that's too low. Velocity too low. Oh. You see, this bottom is not flat, right? If we velocity too low, smooth. You see that? Although it's not good. Now let's see in gather by gather. I mean, after migration, we generate image gathers, right? So you can see here, the velocity too low. You have curved, right? So the short point here, point here, point here, point here. So there's 6 different shots. There are 6 different shots. If we sum them together, the stacking will be misstacked, right? Because this curve is not flat. Okay, it's supposed to be flat. That's the wrong velocity. But if there's no velocity error, you can see flat events. Here you also have a structure here, flat events. And then you sum all the images together, you get a good result. So depth migration velocities. First of all, you imply we have a good subsurface model, the Earth model, right? That means we need a geological implementation. You should try to incorporate the geological implementation into the model before you do migration. And how to get a velocity model? Usually we use a Kirchhoff migration. Right? We generate, as we said, Kirchhoff migration. We can generate in the Kirchhoff migration the image getter. We can keep the offset information. Remember, I said that. If we keep the offset information, you can see the reflection for the same point, same depth. They are flat or not. If not, overcorrected or undercorrected, and then you tune in, adjusting the velocity model. So you do the iterative. Why we do not use a wave equation method to do that? A, wave equation method does not keep the offset information. B, wave equation method is a global method, so it's very time consuming, right? So Kirchhoff migration is best way to do the velocity analysis for migration velocities. The assumption here say for individual points, individual deflector, the image should be flat. Based on, if it's not flat, you just make an adjustment. That's the key. That's the key. So one for technology called tomography actually start from here. When they have a curved travel time, so they have a time residual, and then you based on time residual to work out the velocity variations, velocity changes, and then you refine your velocity model. This traditionally called tomography, right? But actually, that's the very early tomography. But nowadays, we use a whole wave field of tomography, right? Let's show you examples. Here, 3 gathers. That's offset direction. That's the different depths. That's if here you can see they're all flat. That means you have a good velocity. But another thing we show here is, although they're good, flat, but structure not right. Why? There's another thing called anisotropy effect. Anisotropy effect means your wave travel vertically or different angle, you have different velocity, right? Velocity depends on the travel angle. That's called anisotropy. Anisotropy, right? And for velocity model, for the velocity, migration velocity, we should do time migration first and then do depth migration, right? Because time migration can use a smooth velocity model and then gradually refine that, get a more detailed velocity model, right? So time migration, you start from stacking velocity, NMV velocity, you start with that, and then NMV velocity is equivalent to RMS velocity. So you can convert your stacking velocity to layered velocity. This formula is called Dix equation, DIX, Dix equation, right? Based on the different depths, average velocity, you work out the interval velocity. That's okay. And then because you have layered velocity, which means you have layered model, then you can use depth migration. Okay, that's the way. In the depth migration, you start with a Kirchhoff migration, because you do have an offset information, and then based on the residual time, either flat or not, you can further adjust the velocity, right? Refine the velocity model, and also incorporate your geological interpretation result into that, right? So that's the way you do the step by step. Because depth migration need an interval velocity, as I said, need an interval velocity for the theoretical analysis, you should use a true velocity model to the migration, right? So anyway, if we use a smooth velocity to the depth migration, you only use that only as like initial steps, but finally, the final result final image, you should use the layered velocity with the complicated whatever the structure there, right? You should not smooth that. And the velocity you can also include in terms of ray tracing or in terms of wave equation. You also can include anisotropic parameter into there. So velocity varies in the travel time calculation. Use anisotropic economic equation to the travel time, or in the wave equation use anisotropic wave equation to the wave propagation. So this is basically the lecture 8. So very fast. So what we learned today, we have 4 parts. So one is we're talking about the Prestack migration. Why we do need that? Because in the subsurface structure, we do have for a single receiver, single source receiver point, we do not only have a reflection from a single point, maybe from a side, right? We have a flat layer, but also have a dip layer. That's complicated. But even for the single layer, this single layer very likely have a dip angle, right? So we are not overdue, right? But why people waiting for? Okay. But anyway, so the complicated subsurface structure, we do need to do the pre-stack migration. Post-stack migration will use as an initial step, right? So we do NMO first, get the velocity, and then use this velocity to do the post-stack migration, right? And then we based on this velocity, we use Dix's equation to convert into the layered velocity, and then incorporate the geological information into the model. We generate a velocity model, and then use a Kirchhoff migration in the Prestack to generate the offset dependent image getter. And then we use that check. We check the flatness of common image reflection, whether it's flat or not, to adjust the velocity model and refine that iteratively. When everything done, when you try to produce the final result, we just use reverse time migration to get the final result, one go. Because reverse time migration does not give you an opportunity to refine your model, right? Okay, so this is the step-by-step processing. Depth migration is the key. Although typically for the post-stack migration, although we display the result in the time domain, but in fact the procedure itself is depth migration, because if you need exactly the depth point, X point or Z point, you know, and then you know the travel time, right? Why we display in the time domain, rather display straight away in the depth domain at a very early stage, because we do not know the velocity right now. Very likely velocity is not right? So for the post-stack migration, you can use a smooth model, smooth velocity to do the migration. That means we can have a rough idea of subsurface structure, right? And for geological implementation, of course, you can convert your time back to the depth. You have a geological structure, but it's not necessarily right. Okay. So the whole procedure, either post-stack or pre-stack, the methodology is based on the depth, downward continuation, right? Downward continuation for pre-stack, post-stack. But for the reverse time migration, of course, that's you need exactly depth point. We also reviewed migration methods. As I already said, we do need all these methods in it, just like tools in your toolbox, right? you do need, for real data processing, you do need to use all of them one by one. And finally, the migration velocity is the key. So after this, I just in this lecture, I mentioned that at least there are 3 research directions, right? The most ultimate research direction, research topic is you do the migration in a velocity independent way, right? If I expected any of you from this lecture room or from whoever online eventually discover a method to do that, right? You know, it's just like a joke, right? You do know exactly velocity model, and then you do the imaging, right? Your imaging always follows velocity model. So if the model wrong, you cannot have the right solution. That's true, isn't it? Okay. But that's my generation's job. So next generation, I did set some incremental research direction, but the automated one is is seismic imaging without data. Let's say data driven. I just got the data, but do not have a velocity model. You do the migration. That probably is an automatic target. So now I finished the edit sessions. Let me just have a quick view of the 8 sessions. Next week, I'll ask Rob Allen to give you a review for this one. I already passed on my review session PowerPoint to him in the past. What I did the review, I just simply went through a number of previous papers, like step by step. But today, I just try to outline what we learned in this course. If you recall that at the very beginning, I said we have 3 objectives for this course, right? Most importantly, is the third objective, means you understand the limitation of each step. Seems negative, right? But it should be, I think I'll emphasize that because we should be realistic. We should be realistic, right? And also give you the open mind, open eyes for the further research direction. Right? So the objective 1 was for this course. After this course, you should be able to generate stack section and migration section. Stack section is a sort of intermediate result. It's not a final. It's not final. In terms of processing, stack section, for the migration part, stack section is the data for migration. But for processing, of course, it's output, it's a model, right? So it's the data, it's not a model. Let's see what we did here. First of all, we're talking about the seismic acquisition. Unfortunately, we do have no chance to the field. However, I showed some movies. 3 things I think I should emphasize. A, we learned a very quick way to derive a discrete Fourier transform based on Z transform, right? So Z transform is a polynomial. It's a polynomial. For each term, the coefficient is the amplitude of the sample. And the power of that is the index of time, right? That's very straightforward, Z transform. This Z transform is very important for the whole course here. I just give you examples, right? This is one thing. Secondly, for the acquisition, we do need we should realize in the field, the receiver we said single seismic trace, right? But the receiver never be single receiver. We actually has a group receivers. Why we do that? Because we try to get rid of somehow suppress the lateral variation, the horizontal components. That's a denoise in the field. The third one, we're talking about a wavelet. In seismic data, we're talking about wavelet, but a wavelet is a combination of all lots of different components. For example, you have a source signature, you have a source side of a ghost, you have a receive side of ghost, you have a wave propagation effects like attenuation, dispersion, right? And small internal multiples, all this effect. So you should not think about a wavelet as a seismic source. No, right? It's not. So seismic wavelet is a combination of all these elements. I think these three important elements for the first session. For the second session, I use the Z transform to derive one thing, so-called the bandwidth of your seismic data, the bandwidth. Because you have a direct wave from the source downwards, but you also have wave propagating to the surface and the reflection back. So they have a time lag in between zeros, right? You only have 2 points, so-called dipole field. We use a Z transform to the dipole field analysis and convert that operator into the time delay operator, and then we come out so-called sinc function, if we remember, right? Sinc function gives us the first notch of a wave frequency, the frequency spectrum. So the notch gives you the limitation of the spectrum. Instead of ideal wide spectrum everywhere, but you have a notch. So that means that your band is limited. That's important, right? That's the second part. The most important thing is this. The third part, we're talking about multi-channel processing. Multi-channel processing, actually including acquisition in the field, it should generate redundant information. Because we need redundant information for velocity analysis, for different coherent noise attenuation, for incoherent noise, random noise attenuation. There's many mathematical formulas. I think only one is thanks to the great scientist Einstein. He told us you stack n times n traces, you end up with noise reduced by 1 over square root of n, right? That's the only single one. Deconvolution and the filter, they are same thing, but in a different domain. Deconvolution is based on the superposition. The principle is superposition, and then we use Z transform. If you remember, I have a one-time series Z transform of one-time series, and the Z transform of another time series. If we multiply the two Z transforms, we end up another new Z transform. The coefficient is the convolution, right? So that also tell us if we do a convolution in time domain, that's equivalent to the multiplication in the frequency domain. That's important because in the frequency domain we can use a fast Fourier transform to the Fourier to the transform, so-called fast FFT to the Fourier transform. So that means we can speed up all the processing steps thanks to the fast implementation of a Fourier transform, right? But all this came from the example I show you, the multiplication of two Z transform series, two Z transform polynomials, okay? And I said that convolution and the filter actually is in a different domain. Convolution means convolution in the time domain, but in the multiplication, in the frequency we call filtering, right? Now, when you treat the subsurface effects as a convolution operator, you try to remove that. That's called deconvolution. Deconvolution is the words only used for the seismic community. That's basically remove the convolution factor, right? Now, here again, we use a Z transform series here. Why? Because when we do the deconvolution, when we do the inverse filter, which means 1 over a dipole filter, we need the Taylor expansion to be converged. So this convergedness leads to the concept called minimum phase. If filter is minimum phase, which means the Taylor expansion should be converged, otherwise not, right? This is why we need minimum phase. It's easy, right? If it's not, if the dipole is not minimum phase, we can simply swap the two elements. They only change the phase, but does not change the total energy, because the total energy is a squared plus b squared, so always the same. Right? So that's the very important concept. It's a minimum phase filter. Why we need that? I repeat it, because the inverse filter will be converged, otherwise it cannot do that. That's in the chapter 3. And based on the multiple channel data, multiple traces, we do the velocity analysis and the stacking. So the redundant information here, which I exploit to do the velocity analysis, to the random noise attenuation, to the coherent noise attenuation, right? The key equation here, only single equation, is a hyperbolic equation. T squared equal T naught squared plus an m term. So the whole formula here, I think a whole lecture here, maybe 2 equations, 3 equations actually. I already missed the one. When we're talking about acquisition, the sample interval at delta t should smaller enough follow the next row. So delta t should be smaller than next row. So next row is 1 over 2 delta t, the maximum frequency. Why I mention that? Because when we do velocity analysis, there's also analysis issue when we do stack. So delta x also should follow the next row, right? That's the delta t, delta x follows next row. So if the data you have are illicit, you have no chance to recover. So you must do that right at the beginning. So you do not sort of absolutely desample your data. No, don't do that. If you desample that, you will end up in trouble because you never ever go back. For multi-channel filtering, we talking about autocorrelation and cross correlation. Make a linear equation. That's called a Wiener equation. Right? That's the multi-channel filter. And in terms of multi-channel filter, we're talking about 2 typical seismic processing filter. One is called a spark deconvolution. It really means you on the right-hand side, you do cross correlation. You try to cross correlate to the single spark, which means your ideal output with single spark, right? You keep the single spark unchanged. However, if you want to keep a certain segment unchanged, that's called a gap decon, which is called a predictive decon. So gap decon means gap, you keep a gap untouched. Predictive decon means you predict the multiples are predictable, right? So because this deconvolution multi-channel filter, these filters are based on the cross correlation and the autocorrelation, so you actually can check your result by the correlation image. You can see whether it's correlation is good or not. And the 2 deconvolution, predictive decon and gap decon, actually they use the same identical software. Only difference is you set up the gap. If gap is 1, that's a spark decon. If gap is a certain like 32 milliseconds, that will be will be like a particular decal. We need to talk about noise removal. Noise removal, mainly we introduce a number of mathematical transformation. One is we call that tau p transform. Tau p transform in the other field, they call radon transform. Radon transform means that measures the distance and the angle. They call radon transform, right? But in our field, we just measures dipping angle. So we call it tau p transform. Tau is interception time. P is the dipping angle, right? And then further, the tau p, in our field, we call the radon transform, means what we do radon transform, right? That's slightly complicated. The seismic data, in the seismic data, the reflections, including the primary and the multiples, they are in the hyperbolic curves, right? Hyperbolic curves. But because it is hyperbolic curve, it's very difficult to use Fourier transform because it's squared, right? So after NMO, your hyperbolic curve becomes a parabolic. So the variable is no longer square. Variable will be just simple t. That means you can use a Fourier transform, right? So for multiple removal, we just do the NMO and parabolic radon transform. And then you separate the multiples from primaries. Because it's a transform, ideally should have integrate from negative infinity to positive infinity. But our seismic data always have limited offset, right? We have a boundary. The aperture is a limit. Aperture is a limit. So how we do? We do the least square method. We reform the formula from a forward problem to the inverse problem. That's it. And then today and the last week we talked about migration because this we just learned recently, so we will have a fresh mind on that. I do not repeat it. But anyway, so next week we'll focus on the previous papers. I think it just depends on how quickly, how many questions you ask. So at least in my experience, I can have like 2 papers, one in the previous year, 2 papers go through. And nevertheless, you can go to online to find my previous papers with called standard answers. If you have any questions, send the email to me and to Robert, and also to the 3 TA here. Okay, I think this is the end of my lecture here. All the best luck to your examination.